study, and then the concepts we are going to apply to our tutorial questions. So we are going to talk about the wave function again, and now we consider another probability of particle in a box in terms of the tumbling effect. And then for the number, will be we will review this again, and then X-ray, and then finally the stimulated emission, which is the laser. Yeah. So let's first start with this wave function. So as you know, when we are given the wave function, then we have the information of small particle, isn't it? So when wave function is defined, then we have the information of the small particles. Now, this small particle can be an electron, for example. Now, electron actually traveling, and then in quantum physics, we know that such a small particle, the movement, can be now illustrated as a wave function. Yeah. So we now use the wave to describe this small particles movement. So because of that region, we have a kinetic energy. Okay? Because although we use a wave function, but we actually describe the small particle. Yeah? So we have the kinetic energy. And then when this electron traveling in some space or whatever, we might have some potential energy. Yeah? In that space. Okay? Or in the system we have the potential energy. So when you add up the kinetic energy and the potential energy, this will give you the total energy. So in our context, we use this genetic equation to calculate potential energy in most of the cases. Okay? Potential energy in most of the cases. We can do that because wave function is given. Okay? So we are going to give a wave function, and based on that, we will solve this genetic equation to find the potential energy. And then I like to highlight this again. Alright, so when a region of interest is given, then you can always find this probability of finding the particle in the region by calculating this. Okay, you are going to integrate the pair of the wave function within that interest region. Yeah. So now let me talk about this particle in a box. So this diagram is now very familiar to us, isn't it? So this vertical lines represent the potential well, and then this horizontal dashed lines represent the energy state for this particle inside the box. Right? So this wave function inside this box is given as this sine function, and then we already learned about this in the last week. So you may now, if you have a good eye, you may notice some difference, okay, between this diagram and then the previous diagram. So the difference is this. So previously, our wave function has zero probability at the boundary, isn't it? And then the wave function was low negative. Alright, when it's excited to the upper level, again, at the boundary, the probability was zero, and then it was low negative. Yeah? But now here, you can see that there is some hair extending outside of this box, and then we call it tunneling effect. Alright? Now, as you can easily see, we can define a wave function for this hair as this. Your wave function is going to be exponentially decreasing outside the box, which also physically makes sense. It's going to be more difficult to find the particles outside the box. Yeah? Then this diagram is now we don't in terms of the actual probability, then our wave function inside this box is going to be given as this, and then the probability to find this particle outside the box is going to be found using based on this wave function. Yeah? So outside the box, our probability is going to be calculated as the fair Alright? Now let's assume that this wall thickness, this wall has some finite thickness. Okay, let's say this wall thickness is L5. Then this equation is going to be rewritten as minus 2C L prime. Okay, so the probability of finding the particle after the thickness of the wall. Yeah. Then we call it tunneling effect, and then we can also treat it as the transmission, isn't it? So we now use some kind of ray optics. Okay, ray optics. So the light or the wave inside this box now going through this wall. So we have transmission. Okay, transmission. So this is now related to the transmission. So our transmission is approximated as exponential minus 2C L. Right? And then if we have a transmission, then we can also define reflection, isn't it? So again, we use this ray optics or wave optics of classical physics. Okay? So let's say that we have some transmission, then this light will be reflected by this wall and then captured inside the box, and then we call it reflection. Okay? And then because the total probability of reflection and transmission must be this whole number. Yeah? So we are going to say that transmission plus reflection is going to be 1. Okay? We can always find the particle inside the box or outside the box. So they are nicely summarized here, and then in your lecture note, this constant C is also given as this. Alright? So what is U here? This U is your potential energy over the wall, okay? This is your potential energy. And then what is this E? This E is the energy over your particle, okay? Energy over the particle. So I have a couple of questions for you. So particle has a total energy that is less than that of potential barrier. And then when the particle penetrates the barrier, if the wave function is positive constant or exponential increasing, oscillatory exponential decreasing, or none of above, what should be the correct answer? So what do you think? So outside the box, how you describe your wave function?
有的，没有。你看宝前可能是宝，这是第一个排路，还是第一个混沌？
It's just a review this, yeah? So outside the box, so how your wave function is described? Well, I know you have the answer, so just help me. So what's the answer, yeah? B, okay. D, okay, sorry, D. So any other suggestion? No? So we all support this answer, yeah? So you're right, so correct answer is exponential decreasing, isn't it? So after the box, the chance of finding this particle is going to be exponentially decreasing, become more challenging, yeah? So since, because those are the probability is described or expressed in the mathematics, yeah? So let's try to define those, okay, as a wave function. So if we want to consider positive constant, how are you going to express this in the mathematics? So your wave function for constant value is, let's say, wave A, the constant value, isn't it? and the exponential increasing, then your wave function is going to be, let's say, a exponential small ax. Yeah? Then exponential decreasing, and we know this is going to be a exponential minus ax. Yeah? Then what about this oscillatory? How are you going to put it in the mathematical expression? Your wave function is going to be a exponential I ax, isn't it? So you have to have this complex number, yeah? So if you have a complex number, it's an exponent, then it's oscillating. Because this is expanded to the sine function as well as cosine function, yeah? So you can have a positive the number complex number, or you can have a negative complex number too. But anyway, it's going to be oscillating, yeah? So the correct answer is D, and then let's move on to the next question. So now let's consider electron, proton, and alpha particle. Each track separately in identical boxes. Each particle has the longest wavelength when the system is in the ground state. So those three particles are captured in the exactly same boxes, okay, identical boxes. So then which one has the longest wavelength? You can be wrong, yeah? So all of what's your just follow your intuition, yeah?
Ala alpha 没有看到，没有，没有，我跟你讲没有啊。
Don't worry, you can be wrong, yeah? So what do you think? Is the correct answer? Or which ones do you want to support? You like the electron over proton or? B? Okay, so we have one vote for B. B or D? No? So any other answer? So we also vote the answer B. If you think some different idea, please vote now.
Delta B.
B. Alright?
Why?
So let's see. The correct answer is D, isn't it? Yeah? Because your box length is determined, then your wavelength is going to be found as 2L over N. And then N is your energy state, isn't it? Therefore, we are going to have the same wavelength if the box is identical, or the boxes are identical, yeah? So, and then, now I'm going to twist this question a little bit differently. Then, which particle has the highest energy?
它应该是 energy state。哦，所以那个是 N。N 这是 Is it M or N? Why is it M? Right? It doesn't make sense to be N.
Now, this is replaced by N.
Should be N.
So, which one has the highest energy? What is the correct answer? It's going to stay D.
No, D.
So, what's the energy equation? So, you can actually use your list of formula. Yeah? I also don't memorize this, so let me use this, have a look at this list of formula. Our energy in the box is described as a square over 8 ml square over 10 square.
I think it's
Alright, so this is the energy of the particle in the box. So which one has the highest energy then?
Then 下面有个 M。
Yeah. The answer is going to be A, isn't it? Electron, because electron has the smallest mass, yeah? Therefore, the answer is going to be A. Very good. So, I'm going to torture you, so I have one more question. So, particle in a box, yeah? Makes a transition from n equals to 3 to 2. It then makes has a transition from 2 to 1. Each transition results in emission of the longest wavelength. So 3 to 2 and then 2 to 1. So we compare two transitions. Yeah, each one gives you the longest wavelength.
I'm talking about just now your one is what chapter? Chapter A.
Well, we are going to use the same equation, isn't it? So this is the energy at the energy level of n. So each transition will give you the longest wavelength.
What? First.
It's a bit challenging. So let's first have a look at let's try to find this energy gap between 3 and 2. Yeah. So our energy gap between 3 and 2 is going to be E3 minus E2, isn't it? And then, because this is just a constant, okay, so this is going to be proportional to this state of this square difference in the state square, yeah? So 3 square minus 2 square, what is this?
C, right? First
4?
A.
5, okay, very
This one
good.
is
Now let's try the
This
second
one
one.
is
Now 2 to 1, this is going to be
Remember the way
E2
we
minus
draw the-
E1.
Actually, the n
Still
square.
proportional to 2 square minus 1 square, what is this?
N should be.
3, very good. So then, which transition will generate higher energy? This one, isn't it? Higher energy means this is related to H times F, isn't it? So higher energy means the frequency is short, okay? Well, so the frequency is fast, therefore the wavelength is short. Yeah? So the correct answer is the second transition, yeah?
They go up. Yeah.
Right?
Move on time.
Because energy is low,
Move on time.
therefore the wavelength
How many
is
square
going to be
now?
longer.
8 plus.
So the correct
Yeah.
answer is the second one.
850.
Alright, so now
Yeah.
let's move on to
Actually, wait.
the next topic, which is the quantum states of the electrons.
Quite big, sir.
And then some of you already, most of you already learned about this in your EE 1003. Yeah? So let's take this opportunity just to review these quantum state numbers, alright? So we use coding from the quantum numbers to describe the electron configuration or the state of this quantum state of the electron. And then I just try to illustrate those different quantum numbers here. So we first start with this the principal quantum number. So principal quantum number is those energy levels we used, okay, in our previous tutorials as well as in our previous discussions. So this is the energy level, for instance. In the course the hydrogen atom model, we have this proton, and then around the proton, the electron is in the orbit, yeah, and then the first orbit has the energy, the energy state of 1, and then the second orbit has the energy state of 2, and then those orbits, okay, with energy of 1 and 2, actually refer to these principal quantum numbers, alright? And then when this principal quantum number is fixed, then we already know which orbit we are talking about, right? Then once the orbit is determined, we will look at the angular momentum quantum number or orbital quantum number, which will define the shape of the orbital. Okay, shape of the orbital. So when L equals 0, this is most likely sphere. And then when L equals 1 becomes 1, then we talk about this shape, yeah, two rows actually connecting each other. And so we will define the shape of the orbiter. So this inside this big primary orbit, we can have the different shapes, alright, as a subshell, and we also call this subshell. Okay, so this is shell and this is subshell. Then, we use these magnetic quantum numbers to define the orientation of this orbit. For instance, when the angular quantum number is 1. So when we consider this two rope structure, then we define its orientation in the x, y, z coordinate. Then how many unique orientations can you find in x, y, z coordinate? So this is our shape. Then how many of unique orientations you can define? Well, 3, yeah? X, y, and then z, yeah? So we have 3. So that's why when the angular momentum is 1, then we can have 3 the magnetic quantum numbers. And then under the same magnetic quantum numbers, where the electron can spin clockwise or anti-clockwise, yeah? So we can have always 2 different the spin states. And then, while this principal quantum numbers is going to be, we will have this integer, positive integer numbers starting from 1, yeah, 1, 2, 3, and 4. And then this angular quantum number will have positive integer number again, but starting from 0 and all the way to n minus 1, yeah? And then your magnetic quantum number has more variety starting from minus L all the way to the plus L. And then our spin number is going to be plus 1 or 2 or minus 1 or 2, yeah? And then we can use these 1, 2, 3 integer numbers, but sometimes we can also use this the alphabet, yeah? So for these principal quantum numbers, we use a large this alphabet, so starting from K, L, M, N. And then for these angular quantum numbers, we use a small the alphabet, yeah? S, T, E, F, right? So like this is another some illustration of the kind of visualization of these quantum numbers. And then I already explained you when we have the one of the angular quantum number, then we consider very simple structure, and then they can actually have 3 different unique directions. But when it's expanded to second quantum number, the angular momentum quantum number, then we have a more complex structure, which will generate more number of unique orientation. Yeah, so it's expanded to it will expand it to more the magnetic. So this gives us the hierarchy of these quantum numbers, therefore.
Then the metal one.
So when we start with this principal quantum number over 1, and then under this 1, the allowed angular momentum quantum number is 0. Okay? And then under this 0 of this angular momentum quantum number, we are going to have only one magnetic quantum number, and then we follow this route and then we assign 1s. We just denote this 1s. Number 1 comes from this principal quantum number, and then this s comes from our angular quantum number. Yeah. Now let's move on to the second principal quantum number. Because our quantum number now increased to 2, therefore there are 2 different angular momentum quantum numbers around here. So it is 0 and then 1. Let's try to let's follow this path first. Then with 0 angular momentum, we are going to have 0 magnetic quantum number, and then following this route, we will denote this route as 2s. Okay, 2 comes from the principal quantum number, and then s comes from your solution. Yeah? And then let's follow this route. Then we will have 2, 1, and then under this one of this under this angular momentum number, we can set 3 different magnetic quantum number. Yeah, -1, 0, +1, and then follow this route is going to be denoted as 2p. 2 is originated from this principal quantum number, and then p is actually we're accounting for this angular momentum quantum number. Yeah, solution. So you can use this to calculate or figure out those numbers of the quantum states. And then we will use this kind of the table, yeah, to fill these electrons. So we just will list these this quantum the states, yeah. So I will write here again 1s, and then when you move to the second principal quantum number, it will be 2s, yeah, 2s, 2p. 3s, 3p, 3d, and then you can expand it to the first principal quantum number or fifth. Then the sequence to fill the electrons, fill this state with electrons goes like this. So we will use this arrow. So we will fill this 1s state first, and then followed by this arrow, where we will fill this 2s. And then we will have another arrow which indicates that we must fill this 2p first, then we will move on to the 3s. Yeah? So we will follow this arrow direction to fill this quantum state with the electrons. So I have a couple of questions. How many possible subshells are there when n equals 4? Yeah? So how many subshells do we have? So subshell means we are talking about this angular momentum quantum number, yeah? So under principal number of 4, how many L do you have? Confusing? So shall we try together? So when n equals to 4, our L starts from 0, isn't it? 0, 1, 2, 3. So we have all together 4. Yeah? So the correct answer is 4. Now let's move on to the next question. So now our principal quantum number is given as 5. Then how many different values of the magnetic quantum number are possible? So how many magnetic quantum numbers can we have? So well, let's try again. So when n equals to 5, then how many angular momentum quantum number do we have? So we are going to start with 1 or 0. So when the principal quantum number is given as 5, how many these angular momentum quantum numbers are allowed? If it's confusing, we can just write down all these possible numbers, their possible values. So how shall we start with, which number shall we start with? 0 or 1?
9.
Uh-huh.
How is that?
9 นี่กดเต้นนี่เฉย
So shall we start with the 0 or 1?
Okay, I come on.
minus 4 to 4
Let's go.
Because each number got plus and negative also 2, 4, 6, 8, 10.
Zero.
The simple question is
Zero
0 or 1. So
Zero counter.
which number shall we start with?
counter
Very
0.
Uh-huh.
minus 1 actually do minus 1.
Well, it's a bit early morning, so it might be shy, but yeah. So well, please help me. So 0, yeah. So 0, and then 1, 2, 3, 4, yeah. And then which number of this angular momentum will give you the largest variety for this ML?
那个 n
Of course, the 4, isn't it?
这是可以
So
minus
4,
4
our ML is going to start with minus 4, isn't it? Minus 4,
可以笑
minus 3, minus 2, minus 1, 0, and then 1, 2, 3, 4. How many magnetic numbers do we have?
Zero counter.
9, very good. So altogether we have 9.
I
Yeah?
also thought 0
So the
correct.
correct answer is 9.
You know how to do this.
I'm going to move on to this
Like
X-ray.
too easy. I
Right?
don't
So,
You don't want to start doing that. It's like,
Uh,
don't come out like that.
X-rays are emitted when high energy electron or any other charged particle goes wrong. Okay? That's our target. And then in our most of our content, we will consider these K lines. Alright? So this K line, as the name suggests, K line is associated to the K shape. Okay, K shape. So in other words, the principal quantum number is 1. So we are looking at the innermost shape. Okay, innermost shape. So these lines are related to this K-shell, which means we have some change in the electrons in the K-shell. Alright, so let's have a look at this diagram. Along this horizontal axis, we have this wavelength, and then along this vertical axis, we have this intensity. Alright, so let's assume that this electron has a very strong energy. Alright, and then this actually bombard on this metal, and then its energy is strong, kinetic energy is strong enough to kick out the electron in the K-shell. Okay, so this energy is very strong, and then it actually kick out this electron from the K-shell. Then we have a vacancy in the K-shell, isn't it? Then this vacancy is recognized by the other electrons in the above shell, and then the electron, for instance, in the L shell will drop to this K shell to fill this vacancy. Why this electron in the L shell want to drop down to this K shell? Why this electron just stay in the L shell? Right? Instead, why do you think the electron want to fill this vacancy in the K shell? Because your energy in the K shell is smaller. Okay, it's lower than the above energy state, isn't it? Therefore, the system wants to be stable and then reduce this energy. Therefore, the electron in the upper state want to come down to this lower energy state, to be stable. So, when we have this transition from this L shell, okay, to this vacancy in the K shell, then this will generate this K alpha line, which is also shown in this diagram, right? And then, of course, as you can imagine, this vacancy can be filled by the electron from the M shell, which is above level, alright? And then when it fills this vacancy in the K shell, then we are going to have this K vector line, alright? And then between K alpha and the K vector line, Pg1 will have higher energy. So K alpha, K vector, Pg will give us a higher energy. So we talk about this energy drop between two adjacent energy levels, and then K vector means we have a much wider energy gap. So Pg1 will carry higher energy. Beta, the obvious here, K vector will carry higher energy. Therefore, K vector line will appear in the shorter wavelength. Makes sense, yeah? So we have K vector line in the shorter wavelength. Now, we understand their occurrence of the K alpha line and the K vector line in the diagram. Then we have another, this baseline here, isn't it? We have this baseline here. So this baseline is originated from the electron, the incident electron. Alright, so electron is in the motion, is traveling. Now in the quantum physics, we use a wave function, okay, to describe this small particle, isn't it? So when this electron is traveling in the space, we actually consider it as a wave traveling. So in other words, we have the electromagnetic wave traveling in the space. And then when this electromagnetic wave hit this metal plate, its energy is going to be converted to the heat. Okay, so this metal plate is going to be hot, get hot. So this kinetic energy, okay, is converted to this heat energy, alright? And then, because our kinetic energy is described as an electromagnetic wave in the quantum physics, so therefore we have this electromagnetic radiation as a baseline. Make sense here? So when the electron, when the wave lose its energy, now it generates its radiation, right? So AY 19, 20, and so on.
第二个是
The figure on the right shows the X-ray spectrum emitted when the 37 kilo electron volts electrodes bombard a molybdenum target. It contains a broad background with two sharp peaks A and B, which belong to K-band. Explain the physical origins of the broad background and the two peaks. Identify which peak is K alkaline and give your region in terms of the peak position and the relative emission intensity. We actually discussed about this just now. Okay, just now. And then I just want to show you this solution. It very well articulate our discussion just now. Yeah. So let me just read this question. All right. So the broad background of the X-ray spectrum is caused by electron deceleration. Okay, incident electrons deceleration. When the electrons bombard on the molybdenum, the electrons transfer its kinetic energy to heat and the EM wave. As the ratio between the heat and the EM wave change from 0% to 100%, yeah, so its energy actually is gradually transferred, okay, to this heat. So EM wave have a broad continuous spectrum. So we have this broad spectrum, okay, depending on the transfer rate. So longer wavelength means most of the energy is already transferred. So that's why the wavelength is very long. And then shorter wavelength. Here, most of the kinetic energy is converted as the electromagnetic wave. Yeah. Because our kinetic energy of the electron is actually electromagnetic wave, so we have electromagnetic wave. Okay, so at this point, this electron is just incident on the matter. Yeah, so that's why the very high kinetic energy is converted. Yeah. Then the smallest wavelength of EM wave, okay, is created from 100% of kinetic energy, alright, of this incident electron. And then K alkaline is emitted by this L shell electron filling up the vacancy in the K shell. In contrast, the K backline is emitted by the M shell electron filling up a vacancy in the K shell. K alkaline should be of smaller photon energy, therefore, but higher intensity than the K backline. Therefore, peak B should be K alkaline and the peak A should be K backline. So, smaller photon energy means K alkaline has a longer wavelength. Yeah, longer wavelength. Now, we have another statement here, but higher intensity. So, let me go back to this diagram. So this now we identify this as K alkaline because it has longer wavelength. Yeah, it appears as a longer wavelength. And then this is our K backline. But then why the intensity must be high? First of all, we already know that the energy, okay, the energy of the K backline is higher because it appears as a shorter wavelength. Right? But then, why the intensity is higher for the K alkaline? We actually discussed a similar thing in the black body radiation. Yeah. So in the black body radiation, the Planck actually come up with some assumptions. Yeah. So I can draw some energy transfer for this K alkaline as this. All right. Between N equals 1, which is K share, and N equals 2, which is L share. This the excitation will generate K alkaline, yeah? And then K backline actually
but I see what's on the
emitted
screen.
between this transition, okay, when N equals 3 and then N equals 1. So this is our K backline emission. So it's obvious that the K background will appear in shorter wavelengths, but then why intensity must be higher for this K alkaline?
看哪都完了。
Why intensity is high for the K alkaline? So what do you mean? What's the meaning of the high intensity for solar energy? So So in the photoelectric effect, we already learned about this. Yeah, there is a frequency which will define this energy. But then when you increase the intensity, then what does this mean? Increasing intensity. Increasing intensity means the more number of photons, isn't it? More number of photons. So according to this diagram, we have a more number of photons accounting for this K alkaline. So why it happened? Well, in our black body radiation, we already learned about this, that under this Planck's assumption, when this energy gap to bridge is small, then it has a higher probability of the transition, isn't it? So, because K-Becker line has much, it will require much broader energy gap to bridge, so its probability is low. However, for the K-alpha line, the energy gap to bridge is smaller, so we have more probability, therefore we are going to have more number of photons generated from this K-alpha line, isn't it? Therefore the intensity is higher for the K-alpha line. And then just to remind you, we discussed about this in the black body radiation, yeah? So this alpha and the intensity again. And then we have this black body radiation. When the wavelength is too short, then the energy gap is too wide, too large, therefore our probability is small, so the consequence of those effects will give this much of intensity. When wavelengths become very long, then probability is high, but the energy of this energy gap is small, so overall effect will give us an intensity very small amount here, and then there is some optimal wavelength where we can expect a reasonable probability as well as reasonable the frequency, reasonable the energy. Now, let's have a look at this second question. Now we want to determine the cutoff wavelength of the broad background of the X-ray. So our cutoff is here, isn't it? So this is our cutoff. Alright? And then how are we going to determine this? Well, the incident electron kinetic energy is given 37 kilo electron volt. Therefore, this at the cutoff frequency, all of this kinetic energy is converted, isn't it? Therefore, our energy is 37 kilo electron volt. This is related to this cutoff frequency wavelength, so Hg over lambda cutoff. So we are going to solve this for the cutoff wavelength here. Therefore, our wavelength is calculated at 33.4 picometer. Okay, very, very short wavelength. Alright, so I'm going back to our previous discussion. So we conclude this X-ray now and then move on to this another key point on this spontaneous emission and the stimulated emission. And then, well, it's very straightforward to follow those the definitions, so I'm going to skip. So now let's start our actual tutorial question, alright? So, in a region of the space, a particle with zero total energy has a wave function as this. Now, A and L are two constants. Find the potential energy U as a function of X. So, wave function is given and we are asked to find the potential energy. Most likely we are going to use the Schrödinger equation, isn't it? So, if I look at this list of formula, then the Schrödinger equation is given here. Yeah, so I'm going to just copy this Schrödinger equation in the paper. So, d square sin x square equals minus 2mh square